Hi, in this video, I'm going to explain to you how to find fractional or percentage uncertainty and use it to solve problems. So first, let me explain a little bit about the concept of fractional uncertainty. Let's say I have an equation that involves three variables, a equal to b times c. In such situation, I can express the fractional uncertainty of A in terms of the fractional uncertainties of B and C. So we can see that the fractional uncertainty of A is the sum of the fractional uncertainty of B and the fractional uncertainty of C. This is also valid if I have a relationship like A equal to B over C. So whether it is a product of two variables or division of two variables, the fractional uncertainty of A will be the sum of both fractional uncertainties of B and C. So this brings us to a few important points. The first is if I have a relationship like A is equal to 2B or any numerical multiplying factor of another quantity B, then there is no effect of the factor on the fractional uncertainty. So this is the first rule. Then in the second rule, if I have a relationship like A is equal to B square, or could be a power of any number, then you can see this as A is equal to B times B. And using the same idea above like this, so I could write the fractional uncertainty of A as the fractional uncertainty of B plus B again. And you can see that this will give me twice of the fractional uncertainty of B. So with this, we can deduce a relationship. If I have an equation like A is equal to B to the power of n, then the fractional uncertainty of A is simply the n multiplying the fractional uncertainty of B. All right, so I have these two rules plus the generic rule as shown above here, and we shall use this to solve some problems below. Example 1. The size of a square is measured to be 5.5 cm with an uncertainty of 1 mm. Calculate the area of the square together with its associated uncertainty. So this is quite a common questions when relating to uncertainty. They will always request you to find a value, like in this case, the area of the square. And then they will want you to find the uncertainty. So there are two parts. The first part, to find the area of the square, is quite straightforward. We can always write down the equation to find the area. In this case, it will be area is equal to L square. And since L is equal to 5.5 cm, so I can just substitute this into the equation to get the answer. Right, so here I got the area of the square. And the next part, I will want to find the uncertainty of the area. So to do this, first, you have to recognize that the relationship involves power, which is L times L. So I got to make use of fractional uncertainty. In this case, it will be delta A over A is equal to twice of delta L over L. So I got to go and find what is delta L over L. And I can get that quite easily because I'm given 1 mm. That's the absolute uncertainty of the length. And this 5.5 cm is the length. So with that, I can substitute the values in, but you have to take note that the absolute uncertainty is expressed in mm, while the measurement is in cm. So you got to make them to the same unit because you are expressing them as a fraction. So for my case, I will just change my 1 mm to 0.1 centimeters over 5.5, and that give me 0.0364. And take note that this value here that I obtained refers to the fractional uncertainty of A. And since I want to find the uncertainty, which means is the absolute uncertainty, I will have to go and find what is my delta A, which I can obtain it easily by taking this multiplied by the value of A itself, which is 30.25. And I will get a value of 1.1 centimeters. And there is something else regarding uncertainty, which is that you should always express it to one significant figure. So here I'll round it off to 1 centimeter. Right. So now I have the area 30.25 and the absolute uncertainty of 1 cm square. Sorry, there's a square here I missed. So if I were to write down the area, it will be 30.25 plus minus 1 cm square. But hold on, this is not the end yet, because we have to express the measurement, which is the area itself, to the same precision as the uncertainty. So this one refers to the unit, and by rounding off my 30.25 to 30, then I add in this plus minus 1, and that is how I can express the uncertainty of the area. Let's look at the second example. The density of a metallic sphere is found by taking the following measurements. Calculate the density of the sphere with its uncertainty. Again, you can see that there are two things I want to calculate. The first is the density of the sphere, and the second is the uncertainty. I will proceed to calculate the density first because that is always the most straightforward process. So density is equal to mass over volume. So I have got the mass from the question, which is 1410, but I do not have the volume. Although I could calculate my volume from the radius. So I will do this next. Volume of a sphere is 4 over 3 pi r cubed. Putting those values in, I will get 179.6 cm cubed. So now I could calculate my density. D is equal to 1410 divided by 179.6. That gives me 7.85 gram per cm cube. Right, so the first part of the solution is done, and now let's proceed to find the uncertainty. Again, recognize that this involves division. So I got to express the relationship of the fractional uncertainties. Delta D over D is equal to delta M over M plus delta V over V. Right? And at this moment, I do not have my delta V over V yet. Right? So I got to go and calculate that. So how do I do that? First, let's make use of this relationship again. V is equal to 4 over 3 pi r cubed. So I could make use of one of the rules of fractional uncertainty to calculate a relationship between the fractional uncertainty of V and R. So delta V over V is equal to 3 delta R over R. All right, because 4 over 3 times pi are just numerical factors and they do not affect the fractional uncertainty. So with that, I could just substitute my delta R over R as 5%. Okay. Fractional uncertainty and percentage uncertainty are quite similar. The only difference is percentage uncertainty. In percentage uncertainty, you have to multiply by 100. Right? So in this case, since this is already given as percentage, I shall proceed to find my answers in terms of percent. So this is 15%. And so from here, I could rewrite my delta D over D as 2%, which is the percentage uncertainty of mass, plus this, which is 15%. So I got my percentage uncertainty of D as 17%. And once I got this, of course, I could just calculate my absolute uncertainty of D, which is 17%. Expressing as a ratio, it will be 17 over 100 multiplied by the value of the density. That will give you a value of 1.33 rounded off to 1 gram per cm cube. And that leaves us with the last step, which is to express the value of the density with its uncertainty. So the density is 7.85 plus minus 1, and I got to round off the 7.85 to units. So that will be 8 plus minus 1 gram per cm cube. All right. Right. I have another example 3 below. I would like you to do it and check your answer from my website. Thank you.